Hello and welcome! In today's video, we're going to be going over topic 4.4, indeterminate forms and L'Hopital's rule. So, we keep on building up these tools. For example, we've been finding minimums and maxes of functions, which are really these extreme points. We've been finding where functions are increasing or decreasing, concave up or concave down. And all of these are very important features when it comes to graphing. And in today's video, we are going to be building yet another very important tool for graphing. But not only that, a very useful tool for limits, interestingly enough. So, to start out, because this is a very limit-centered video, we are going to start out by just working on some limit problems, ones that we know how to work. So, we have the limit as x approaches 0 of the cosine of x cubed. Well, we can direct sub n, and this is really just the cosine of 0 plus 0, which cosine of 0 is just 1, and that would be our answer for our limit. For this next one, we have to do a bit of thinking. So, as x gets really, really big, what we have to start considering here is what really starts to dominate. And as x gets really, really big, the minus 9 and this minus 6, they become insignificant. So what this function starts to look like is just the square root of x squared over 2x. Well, the square root of x squared, we know, is the absolute value of x over 2x. And because x is positive, because we're going to positive infinity, we don't have to worry about it. Then we can cancel this x and that x in the denominator and get 1/2 for the solution to our limit. But sometimes we don't have limits that work out prettily. For example, let's look at the function f of x. So f of x is defined as the natural log of x divided by x minus 1. So let's real quickly take a look at this limit. So we're taking the limit as x approaches 1 of the natural log of x divided by x minus 1. Well, if we plug in 1, we can see that this is going to be a 0 over 0. So, interestingly enough, we don't have a method for solving this. Well, maybe we can try multiplying it by a conjugate. I don't think that's going to do much, because there isn't really a conjugate pair to, try and eliminate, but we can try. So we're going to take the natural log of x divided by x minus 1 and times it by x plus 1 divided by x plus 1. So what we get in the numerator here is x natural log of x plus the natural log of x divided by x squared minus 1. Well, now whenever we plug in 1 into the numerator, we get a different result, which is just going to be, or actually, no, rather, we do still get 0. And if we plug 1 into the denominator, it's still 0. So our methods here just don't work, as there's nothing to cancel. There's no algebraic manipulation. Well, of course, we can plug in values getting closer and closer. However, we want to find an algebraic way of solving these limits. So now looking at this limit where it goes to infinity. Well, we actually do have a way for solving this. And this way is actually going to be further reinforced by what we learned today. So we can do what we just did earlier, where we say that this plus 1 and this minus 1, they become insignificant as x goes to infinity. So it becomes just x squared over 2x squared, which, interestingly enough, has the same exact answer as our second limit that we did. But there is still some functions out there where we simply just don't have the tools yet to evaluate them. And we're going to acquire those tools in this video. So, we have this wonderful rule here. It's called L'Hopital's rule. And what it supposes is if f and g are differentiable and g of x is not equal to 0 on an open interval I that contains a, except for possibly at a, suppose that the limit as the limit as x approaches a of f of x is equal to 0, and the limit as x approaches a of g of x is equal to 0, or the limit as x approaches a of f of x is infinity, or the limit as x approaches a of g of x is equal to infinity. So in these cases where it's f of x, the limit as x approaches a of f of x and g of x are 0 or infinity, or in other words, we have an indeterminate form of 0 over 0 or infinity over infinity, the limit as x approaches a of f of x over g of x is equal to the limit as x approaches a of f prime of x over g prime of x. So, the very first thing we have to do when using L'Hopital's rule is verify that it applies. Well, if we plug in 1 into this function, we see that we get 0 over 0. So we can use L'Hopital's rule. So now what we're going to do is we're going to take the derivative of the numerator and the denominator. Please note that we are not doing the quotient rule. We are taking the derivative of the numerator and the denominator independently. So we get the limit as x approaches 1 of 1 over x, and the derivative of x minus 1, that is just 1. Alright, now if we take this limit, the numerator is going to be 1. The denominator is going to be 1, so the limit is equal to 1. You may have recalled that in a trig video, in fact, whenever we were first learning limits, I suppose that the limit as x approaches 0 of sine of x over x is equal to 1. Well, plugging in 0, we get 0 over 0, because sine of 0 is 0, and x, whenever x is equal to 0, is 0. So let's take the derivative of the numerator and the denominator. So the limit as x approaches 0 of the derivative of the numerator, which is cosine of x, divided by the derivative of the denominator, which is just 1. Cosine of 0 is 1 over 1. So our answer is 1. Alright, for this last one, I think this one may be a small bit of a doozy, but we are going to try to work through this together. So we need to start out by verifying that this is in the form 0 over 0. Well, if we plug in 0 in this top, we will get 0. 3 to the power of 0 is 1. 1 minus 1, 0. So this is, again, a 0 over 0 indeterminate form. I should have probably done one of these as an infinity, but that is okay. We don't have to worry about that. Well, actually, you know, I'll create a problem here in a moment for that. But let's tackle this beast first. So, we take the derivative of the numerator, which in this case is going to be 3x plus the natural log of 3 times by x times by 3 to the power of x, all over the natural log of 3 times by 3x. Well, now if I plug in 1 in the numerator, or sorry, 0, we get 1 plus, well, we have 0 times by, all the rest of this evaluates to 1, so that's just 0, divided by the natural log of 3. So our answer is 1 over the natural log of 3. Very strange. So here I've added one more. So this limit we can clearly see is of the form infinity, or really the square root of infinity, but infinity nonetheless, over infinity. So in this case, once again, we can use the derivative, or L'Hopital's rule. So we say the limit as x approaches infinity, the derivative of the numerator is 1/2 the square root of x divided by the derivative of the denominator, which is 1e to the x. Well, because we have 0 divided by infinity, which we know that this is always just going to go to 0, because this is going to make this go to 0, and that's already 0. So it's just going to go to 0. I hope you can hopefully logic your way through that. So now I suppose I want to look at a case where L'Hopital's won't work. So we have the limit. Well, whenever we're taking this limit here, let's plug in pi. Let's see if it's a 0 over 0. Well, if we plug in pi, we see that sine is going to be 0. Or sorry. And cosine, well, cosine will be 1. So we get 0 over 0 here. Or sorry, actually, yeah. That should be 0 over 2. So in this case, we don't have to use L'Hopital's to evaluate this limit, as it's just going to be equal to 0. However, if you did try to use L'Hopital's, what you'll see is that we're going to get the same, we're going to get cosine over sine of x, which is really just cosine at pi is going to be -1. And sine, however, will be 0. So we get the answer of negative infinity, which is not the answer to the limit here. So unless it's indeterminate, we do not want to use L'Hopital's rule. So now we're moving on to a bit more of an interesting topic here. So if the limit as x approaches a of f of x is equal to 0, and the limit as x approaches a of g of x is equal to plus or minus infinity, then it isn't clear what the limit as x approaches a of f of x times g of x is. This kind of limit is a 0 times infinity indeterminate form. So this happens whenever we're taking the limit of like a function in the form f of x times by g of x. And the way that we're going to fix it is by writing either g of x, or we're going to make this into a quotient, so L'Hopital's rule will apply. So looking at this example here, find the limit as x approaches 0 of x ln of x. Well, as x approaches 0, we see that ln of x is going to go to negative infinity. However, x is going to go to 0. So which is the answer here? Well, what we're going to do is we are going to say that this is actually the limit as x approaches 0 of the natural logarithm of x divided by 1 over x. So now as the limit as x approaches 0, well, the numerator is going to be going to negative infinity. And the denominator is going to be going to, well, technically this is from the right, so positive infinity. So we have our indeterminate form. We have infinity over infinity. So now what we're going to do is we're going to take the derivative of the top and bottom, or apply L'Hopital's rule. So we get 1 over x divided by negative x to the negative 2 power. So, how does this help us? So what we're going to do now is we're going to multiply the top and bottom by x. So we get 1 over negative x to the power of negative 1. And now, as this approaches infinity, this is going to be the same thing as 1 over x. As this approaches 0, sorry, not infinity, this denominator is going to be going to negative infinity. And because we're dividing by infinity, the limit is going to go to 0. So now we have another type of indeterminate form, and it's where we have like infinity minus infinity. So these types of indeterminate forms often require us to use our previous knowledge to solve them. So what we're going to start out by doing is just trying to plug in 1 and seeing what happens. Well, we get for this first one, or for this first half, we will actually get 1 over 0, which is going to be infinity. So the first part of that value, it's infinity. Minus, and because this is an asymptote and we're approaching it from the right, that is going to also be going to infinity. So we see that we have this infinity minus infinity. So what we do to evaluate these limits is we have to use some algebraic manipulation first. So we're going to get a common denominator here. So we get x minus 1 minus the natural log of x divided by x natural log of x minus the natural log of x. And if you don't know how I did that, I just cross-multiplied everything. So now, if we plug in 1, well, we get 1 minus 1, that's 0, minus 0. So we get 0 in the numerator. So we get 0. If we plug in 1 in the denominator, we get the natural log of 1 is 0, minus the natural log of 1 is also 0. So we see that this is 0 over 0. So this is in a form where we can use L'Hopital's rule. So we get the limit as x approaches 1 from the right. Well, the derivative of the numerator here is going to be 1 minus 1 over x divided by the derivative of the denominator here. Well, the derivative of the first is just 1, so that gives us a natural log of x, plus the derivative of the natural log of x is 1 over x, times by x is just going to give us 1, minus 1 over x. Now, plugging in 1, we get 1 minus 1 over 1, divided by the natural log of 1 is 0, plus 1 minus 1 over 1. So we get 0 over 0 again. So now what we're going to do is, because we have 0 over 0 again, we're going to apply L'Hopital's rule for a second time. So we get the limit as x approaches 1 from the right of the derivative of the numerator, which in this case is going to be x to the power of negative 2, divided by the derivative of the denominator, which is going to be 1 over x, plus x to the power of -2. Now plugging in 1, we will get 1 in the numerator, and in the denominator we're going to get 2. So we get 1/2 as our answer to our limit. For this next limit, we have e to the power of infinity, which is going to be infinity, minus x as it approaches infinity, which is also infinity. So we once again have this form of infinity minus infinity. So what I'm going to do here is I'm actually going to factor out a x. So we get x times by e to the x divided by x minus 1 is equal to, well, let's think of it like this. Or rather, let's take these limits independently. So we get the limit as x approaches infinity of x times by the limit as x approaches infinity of e to the x divided by x minus 1. I'm just not going to really worry about that minus 1 part. Well, actually, you know what? There we go. Because, or I suppose I have to, give me one moment. There we go. This is what I'm going to do with it. So I'm just going to turn this into a minus x real quickly. Alright. Now, taking these limits as x goes to infinity, on this right side, we have an indeterminate form. We have infinity over infinity. So we're going to take the derivative of the numerator, and we know that this is just going to evaluate to infinity. So it's just infinity times by, well, e to the x minus 1 divided by 1. As x approaches infinity, that's going to go to infinity. So this limit clearly is just going to approach infinity. Sometimes these limits don't approach any real number. That's important to recognize. So another form of limits where they are indeterminate is indeterminate powers. So suppose that we have a function, we're taking a limit of a function in the form f of x to the power of g of x. Well, there's 3 indeterminate forms that can pop up. 0 to the power of 0, infinity to the power of 0, and 1 to the power of infinity. So, in these cases, the first case is going to occur when the limit as x approaches a of f of x is equal to 0, and the limit as x approaches a of g of x is equal to 0. And that will be a type 0 to the power of 0. If the limit as x approaches a of f of x is equal to infinity, and the limit as x approaches a of g of x is equal to 0, we get infinity to the power of 0. And finally, if we have the limit, and apparently I can't draw an f for the life of me, as x approaches a of f of x is equal to 1, and the limit as x approaches a of g of x is equal to infinity, we get a type of 1 to the power of infinity. So let's go over how to work through these, really. So the way that we're going to start this out is we're going to define a function, y is equal to 1 plus sine of 4x times by cotangent of x. Now what we want to do is we're going to take the natural log of both sides. So we get cotangent of x times by the natural log of 1 plus sine of 4x. Alright, now that we have this function, let's find out what the limit as x approaches 0 of it is. Alright, give me one moment to move this. There we go. Limit as x approaches 0. So, what you might notice is we have a product here. However, we can very easily make this into the form Or actually, I'm going to work this horizontally, as I think this makes a bit more sense that way. So we're going to get the limit as x approaches 0 of the natural log of 1 plus sine of 4x divided by tangent of x. So now that we have this expressed like this, we can now see if L'Hopital's rule will apply. Well, if we plug in 0... Alright, so as we plug in 0, this numerator is going to become the natural log of 1. Well, the natural log of 1, as we know, is 0. And tangent of 0, well, that is going to be sine of 0 divided by cosine of 0, which is also 0. So we see that this is a 0 over 0 indeterminate form. So now what we need to do is we need to take the derivative of the numerator and the denominator. So we have the limit as x approaches 0. Well, the derivative of the numerator is going to be 1 plus sine of 4x times by cosine of 4x times by 4, alright, divided by, and then the derivative of the denominator is going to be secant squared of x. Now we can plug in 0, and we will get an answer of 4 divided by 1 all over 1 over cosine of 0 squared, which is just going to be 1. So we get an answer of 4. So if the limit, so we've now found the limit as x approaches 0 of the natural log of y, we now just have to say, well, now we just have to find what happens as the limit as x approaches 0 of e to the natural log of y, and that should be equal to the limit as x approaches 0 of y, or this original function. Well, we know that the limit, this is the same thing as e to the limit as x approaches 0 of the natural log of y using our limit properties, which we know is just 4, as that's what we solve for up here. So we get e to the 4th is equal to the limit as x approaches 0 of y. So that's our answer, e to the 4th. Alright, for this next one, we're going to use a law of the same steps. So, we define a new function, y, and that's going to be equal to x to the power of 1 over x. Then we're going to take the natural logarithm of both sides. I kind of write the natural logarithm kind of weird sometimes, where I'll write it afterward. That is not proper math notation to my knowledge. Who knows, somebody out there might be using it, but to my knowledge it is not me who endorses it. So, let's see. We're taking the limit as this expression right here goes to infinity. Or we want to know what happens as this goes to infinity, or as y goes to infinity. Well, in this case, we have a infinity over infinity indeterminate form. So what we have to do is we need to take the derivative of the numerator and the denominator. So we get 1 over x divided by 1. Well, taking the limit as x approaches infinity, we can clearly see that this numerator is going to go to 0. Dividing that by 1, we get an answer of 0. And that's our limit as x approaches infinity of the natural log of y. Well, now if we want the limit of y as x goes to infinity, what we have to do is we're going to find the e to the power of the limit as x approaches infinity of the natural log of y, and that should be the same thing as y, the limit as x approaches infinity of y. Well, e to the power of 0, which we know that is the answer to this limit, is equal to the limit as x approaches infinity of y. So the limit as x approaches infinity of y must be 1. Well, I hope this video has helped you with your understanding of L'Hopital's rule. In the next video, we will be going over how to graph functions, which this is really the last building block we need. Well, I hope you all have found this video informative, and if you did, please make sure to like and subscribe. Have one for the rest of your day.